Welcome back. In this video, we'll be looking at example 3.3.6. We're giving a linear transformation on polynomials of degree 2 or less that sends a polynomial to p of 2x plus 3, a new polynomial. I want to find a basis in which TB is a diagonal matrix. I'm going to follow a method similar to this one. All right, so here we've figured out how to diagonalize the matrix A. I needed to find eigenvectors and eigenvalues for that matrix. I'm going to do the same thing for the linear transformation T. I need to find eigenvalues and eigenvectors for it. All right, so to do that, I'm going to find T of S for any basis I want. I'm going to use the standard one, so x squared x1. All right, so I need to figure out what happens when I apply t to these three basis elements, and I need to write them in terms of the basis again. So here I'll take 2x plus 3 and I'll square it. Here I'm just going to take 2x plus 3, and here I don't have any x's, so I just leave 1. But really, I replace x with 2x plus 3. All right, if I expand this, I'll get 4x plus 4x squared plus 12x plus 9. And so when I write t of s, I'm going to put x squared x1 here, and then this is t of x squared, t of x, t of 1. So t of x squared will be 4 times x squared plus 12 times x plus 9. T of x is 2x plus 3, so no x squared, 2 and 3. T of 1, well, it's just 1, so there you go. All right, so I'm going to call this matrix A. And now I'm going to use what we've learned before to find eigenvalues and eigenvectors for A. All right, so I'm going to start with PA of x. That's 4 minus x, 0, 0, 12, 2 minus x, 0, 9, 3, 1 minus x. All right, that's not hard at all because I have a lower triangular matrix. If you want to expand, you could expand first here, then on the second, then on the third, and you'll see everything's going to work well. Or you could remember that the determinant of a upper triangular or lower triangular matrix is just a product of its diagonal entries. And so I have 3 eigenvalues. I have lambda equals 4, I have lambda equals 2, I have lambda equals 1. All right, so let's do 4. I'm going to look at A minus 4i. That's going to be the matrix 0, 0, 0, 12 minus 2, 9, 3, minus 3. All right, so I've reduced that one ahead of time. It's not super nice, so I got minus 1 over 9, 0, 1, minus 2 thirds, 0, 0, 0. And if I took S right here, I would get that x, y, z is 1/9, 2/3, 1 times s. I'm going to take an s equals 9 just to avoid fractions. And so my first eigenvector is 1, 6, 9. All right, and the basis for E4 of A is 1, 6, 9. All right, second eigenvalue. I have 2, A minus 2i. That would be 2, 0, 0, 12, 0, and 9, 3, minus 1. So first row will reduce to 1, 0, 0, and then I'll get rid of the first column and everything else. And so I'll have a row of zeros, and then the middle one will be 3 minus 1, so 1 minus a third. First equation gives me that x is 0. Second, it's 1/3 of s, and then 1. If you like fractions, you could just take s equals 1. I tend to avoid them, so I'll get 0, 1, 3. That's the second eigenvector, and that's gonna give me the generator for the eigenspace of lambda equals 2. And finally, lambda 3 was 1. Let's see, so I would get 3, 1, 0. First row will be 1, 0, 0. Then I get rid of the first column, and there you go. So I still have a free variable. It's z, but the other variables are just 0. And so at s equals 1, I will get 0, 0, 1. So I get 0, 0, 1 here. All right, so I have my basis of eigenvectors for A. I'm going to translate them to get a basis of eigenvectors for T. All right, so I have P1 was 169. And so the first polynomial will be 1 times x squared plus 6 times x plus 9. And that's going to be my first eigenvector. P2 is 0, 1, 3. And so f2 of x is 0x squared plus x plus 3. And P3 is 0, 0, 1. So f3 will be 0x squared plus 0x plus 1. All right, and so the basis that we're after, I claim, is x squared plus 6x plus 9, x plus 3, and 1. So unless we've made a mistake, the matrix of the linear transformation T in this basis, if you start with x squared plus 6x plus 9, then x plus 3, then 1, x squared plus 6x plus 9, x plus 3, then 1. Let's check at least the first. So if I have t of x squared plus 6x plus 9, that's going to give me 2x plus 3 squared plus 6 times 2x plus 3 plus 9. So I get 4x squared. All right, so this one's a 4. And then I have 12x plus 12x, so I get 24x. Oh, sorry. No. All right, sorry, I was getting confused again. All right, 9 plus 18 plus 9, and so I get 4x squared plus 24x plus 36, and that's 4 times x squared plus 6x plus 9. Perfect. I keep forgetting to go back to the basis. All right, if I do the second one, since I've messed up the first, let's do the second one. That's going to be 2x plus 3 plus 3. That's 2x plus 6. That is 2 times x plus 3. And so I will get 0 to 0. And we've already said that T of 1 is 1. Let me put it here. Actually, why don't I shrink it all just put that last little detail so that it is complete. T of 1 is 1, and so I have 0, 0, 1. All right, so the matrix has the eigenvalues on the diagonal. The first one is the eigenvalue of x squared plus 6. Second one is the eigenvalue of the second vector. And the third one is the eigenvalue of the third.